Right, we're now going to have a look at the halogenation reactions of alkenes. So if we're doing the halogenation reaction, we are adding a halogen to the alkenes. They're all going to be addition reactions again, but when it comes to halogenation, we have to look at the reaction mechanism of it. So there are going to be quite a few new things that we'll be covering in this video. So if we're doing the halogenation reaction, we can add a halogen to it, so that can be any halogen. Usually the ones that we use are either Cl2, Br2 or I2. Okay, so they're the ones that we tend to use. The one where we use bromine, that's what I'm going to do in the example, but we can actually use bromine as a test for alkenes. I'm going to show you why we can use bromine as a test for alkenes in a little bit. So let's do firstly the overall reaction. So let's again start off with ethene, like so. And if we react that with Br2, this is going to form, so again it's going to form one product because it's an addition reaction, and we add our Brs to the carbon like so. Okay, so this is the overall reaction. This doesn't need any reaction conditions. It's done at room temperature, doesn't require a catalyst. We tend to use bromine water, which is bromine dissolved in some water. So it tends to have the state symbol aqueous with that. Okay, right, in terms of what you'd observe in this reaction, bromine dissolved in water is going to be an orange-brown solution. Okay, so over here, your bromine water is going to be orange-brown. So orange-brown solution. And at the end, because all of your bromine has reacted, at the end you shouldn't have any bromine left because it's a part of this molecule here. When bromine's in a molecule, it's not going to be the orange-brown colour. Okay, so only when you have bromine by itself, Br2, does it form the orange-brown solution. So that means over here in our product, we lose that orange-brown colour. So it goes from an orange-brown solution to a colourless solution. And that's what you would observe when you add bromine to any alkene. And this is what we use as the test for alkenes, or we say the test for unsaturation. We add bromine water, then if an alkene is present, the orange-brown solution will go colourless. Right, let's now have a look at the mechanism that this undergoes, because the reaction mechanism is the more difficult part of this. So by reaction mechanism, so mechanism is just the step-by-step process that happens. Okay, that reaction that we drew there doesn't all happen in one go. It happens in different steps. So we need to know what the steps are in that reaction mechanism. So first things first, let's also name this reaction mechanism. So the name of this reaction mechanism is called electrophilic addition. Okay, I've already covered what the addition part means. We're going to go from two reactants to one product. Let's focus a little bit on what the electrophilic part means, and just be aware that you spell this correctly in an exam because they do look for the correct spelling. So electrophilic comes from the word electrophile. Okay, and if you kind of break up the word electrophile, so electro part is to do with electrons. Phile means that you like that. So electrophile is something that likes electrons. Okay, so if something likes electrons, it itself doesn't have enough electrons. Okay, it wants to gain electrons because it doesn't have electrons itself. So that means an electrophile, the correct definition of it is an electron pair acceptor. Okay, an electrophile itself is usually electron deficient, so it wants to gain electrons, and that's why it's called an electron pair acceptor. So the way to identify an electrophile is either usually something that has a positive charge or it's delta positive. Okay, so slightly positive. and that's what the electrophile is. Okay, and we're going to show that in our reaction mechanism. I'll highlight to you what the electrophile is, but essentially this addition reaction happens here in the presence of an electrophile. So let's have a look at our ethene molecule. Okay, in terms of our ethene molecule, we know that this part here, so it's a sigma and a pi bond. This sigma bond has 2 electrons in it. The pi bond also has 2 electrons in it. So in total, there are 4 electrons between these 2 carbons, or being shared between these 2 carbons. So that means this area here is very electron rich. There's a lot of electrons here. Okay, so this area here is very electron rich, and that means it is going to attract an electrophile. It's going to attract something that's electron deficient because it has a lot of electrons here. So the other thing in our pot is bromine. Okay, bromine is a molecule. When it gets towards this very electron rich area, we know that something that's very electron rich could induce a dipole along this molecule here. Okay, so if this is very electron rich here, the electrons that lie in this bond are pushed downwards. Okay, so this area of electron richness pushes the electrons here downwards towards this bromine, and that induces a dipole across this Br-Br. So that means this bromine is delta positive, this bromine is delta negative. Okay, so this electron-rich area pushes the electrons down here, and that forms a dipole across the bromine-bromine bond. The one closest to the double bond is Br delta positive. The one further away is Br delta negative. Okay, this here now is our electrophile. We've got this Br delta positive, and that is electrophilic, which means it wants to gain electrons. So this area here is very electron rich. This area over here is very electron deficient. Okay. So the next thing I need to cover is what we call a curly arrow. So curly arrows are something used in organic chemistry that show the movement of a pair of electrons. So a curly arrow shows the movement of a pair of electrons. Okay, and literally it's just an arrow like that. Okay, just make sure it's got 2 lines here. Don't draw it like that because that means something else. It must be a this headed arrow over here. Okay, so we've got our electrophile here. We know it wants electrons. We know it likes electrons. We know over here we've got a pi bond that's weak. Okay, so it's going to break. So our weak pi bond, remember our pi bond also has 2 electrons, that is going to transfer or move to the Br delta positive. And I show that by drawing this curly arrow. So that curly arrow is showing a movement of a pair of electrons. So it's the pi bond electrons here going to that electrophile. So remember what we said, electrophile wants to accept a pair of electrons. I'm showing that by showing that movement of electrons with this curly arrow. Okay, so a pair of electrons are going to come here. And then in that point in time, that bromine has too many electrons. So that means this Br-Br bond must also break. Okay, so to show that bond breaking, I have to start my curly arrow from the bond and it goes to the Br delta negative. Okay, if you remember what we did in the alkane reaction video, with the, both the electrons going to one of the atoms in that bond, that is called a heterolytic fission. Okay, so the bond here is breaking via heterolytic fission, which means both the electrons in this covalent bond are going to one atom. Okay, so I'm now going to show the product of that step in the reaction mechanism. So as we said, the pi bond electrons here are moving towards this Br here. And when it does that, it actually forms a bond between either of these carbons and that bromine there. So I'm going to show the new bond in a different colour pen. So that movement there has formed a bond. As I said, it doesn't matter which carbon you pick in this case. And it's formed a bond between that carbon and that bromine there. Okay, that means the other carbon is missing some electrons. So that means it's got a positive charge. And we call this carbon here a carbocation. So a carbocation is where a positive charge is on a carbon, because as I said, this carbon only has 3 bonds at the moment. It doesn't have 4. When these electrons here went to the Br, that forms a Br minus ion. Okay, so this bromine now has a lone pair of electrons on it. Okay, and now to complete this, we want to show, so we know that we've got to form a bond between the bromine and that carbon. I draw a curly arrow from the lone pair, so not from the negative charge. I should draw a curly arrow from the lone pair here going to my carbocation, like so. Okay, and what that does is it shows the formation of a bond between the bromine and the carbon there. And that means the final step, probably not going to be able to fit this in, but my final step, I have formed that product I had drawn out earlier. Okay, and this reaction mechanism is called electrophilic addition. So all the alkenes will undergo electrophilic addition when you do their mechanism for the halogenation reaction. Okay, so overall, we've gone from 2 reactants to 1 product. We've shown the step-by-step mechanism using curly arrows, and we have shown that it's electrophilic addition because it was a reaction with the electrophile here. Okay, so let's just do another example of this. I'm going to use a different molecule. So I'm just going to go for propene. Okay, I might, when I'm drawing out, I might just keep that as CH3 just to make life slightly easier. Let's do, so not the bromination, let's go for chlorine. So let's do the chlorination reaction. Okay, so whenever you start doing the mechanism, draw out the molecules. Okay, and then the first thing that you need to do is draw the dipole. So the question will say, you know, draw any relevant dipoles and lone pairs. Over here, the chlorine that's closest to the double bond is going to be our delta positive, and the chlorine furthest away is going to be our delta negative. Okay, you then need to draw a curly arrow. So the curly arrow is always going to start from your double bond, so it's the center of the double bond going to the halogen with the delta positive charge. And then the chlorine-chlorine bond must break, and the curly arrow goes from that chlorine-chlorine bond to the chlorine delta negative. The next part of that is this part here. Sorry, let me just draw this out. So we're forming a bond, so it doesn't matter which carbon we pick here. I'm just going to go for that one. So we formed a bond between that carbon and that chlorine there. That means we've got a carbocation on the other carbon. And we also have a Cl- with a lone pair of electrons. Okay, and the final curly arrow is always from the lone pair, not the negative charge, from the lone pair going to the carbon positive, the carbocation. And if we do that, we then form a bond between that carbon and that chlorine. Like so. Okay, so again, this is electrophilic addition because we've got our electrophile here. Curly arrows, remember, when it comes to alkenes, curly arrows should always start from the alkene, from the double bond, going to the halogen with the delta positive. And it's an addition reaction because we started off with 2 reactants and ended up with 1 product.